Hello physics students. Today we're going to find the electric field of a charged disk. In other words, what would the electric field caused by this disk be if I rubbed it down and disturbed the equilibrium of equal number of protons and electrons on this object? Let's suppose I strip an even concentration of electrons off, leaving this disk positive. And what I want to know is what the electric field is along this axis, some distance above the center of the disk. Before we begin that, I want to first ask you, can you state the three main steps that we use for finding the electric field of a distributed charge in this unit? Let me pause the video and give you a chance to think those up in your mind. Okay, so let me show you what they are. Whether it is a charged arc or a charged ring or a line of charge like this or something like a disk, we follow three main steps. Maybe before you write this title, you could just sort of jot these down in your notebook as a summary of the techniques of this unit. So let me pause and give you a chance to jot this down. Okay, so the first thing, we know the only formula for electric field that we have is E equals KQ over R squared. So whatever the shape of the object, we cut it in our minds, in our imagination. We cut the object into tiny fragments such that the electric field of each fragment dE will be KQ over R squared. That formula works because now it looks like a proton or an electron. Then what we do is we imagine that electric field pointing in the proper direction, depending on positive or negative, and we select a proper component if necessary. Why? Well, in the case of this bar, if we imagine a charge here producing a dE like this, as we integrate around this bar, we're going to cancel out the horizontal components. Only the y component will survive. So we select the proper component by using the cosine function in a little triangle over here. But sometimes it's the sine function. So dEx, and I put a little question mark because maybe the electric field's in the y direction or the z direction. Whatever direction it is, we might have to multiply by a trig function to pick the proper component. But this step is not always necessary. Like when we want to find the electric field here, pointing away, if this is positive, every segment of this bar creates an electric field like this. So we don't need to multiply by a trig function to have the proper component. We already have it. And then finally, we integrate over the entire object to get the net electric field. So that's the process. But now, in this topic, we're going to move to a two-dimensional surface. And what you need to do in that case is technically perform two integrals, because we have charge spread over two dimensions. So we can't just integrate over the bar once and we've integrated over all the charge. What we might have to do, well, in a sheet of paper, we'd have to integrate and add up all the parts of the charge with respect to x, and then y to get the total contribution of the entire sheet of paper. So we're going to have to do something similar for a disk. Okay, so let me remove this and begin with today's actual notes. So, maybe I'll move this over here. Go ahead and jot this diagram here. I put it on a piece of paper because I want to recycle it for a later part and I'm going to have to erase it and I don't want to have to redraw it. So here it is. What we have is a disk with a certain charge and a certain radius. That means now it has a charge spread out over an area, not a length. This had a charge density of coulombs per meter. We use the symbol lambda in one dimension. Now we've got spread in two dimensions. We use a new symbol, sigma, also from the Greek alphabet. So this is going to be coulombs per meter squared, the concentration over the area. And here's our disk, looking at it in a perspective. Okay? And what we're going to do is, rather than integrate twice, we're going to recycle the formula from the ring, because we already found the electric field of a ring integrating around one dimension. And that ring right here, a certain thickness dr, will produce an electric field dE in the z direction, okay? Like how I did the r in perspective, okay? So this is capital R, the radius of the disk itself, and this is lowercase r, the radius of the ring, some smaller ring within my larger disk that's creating an electric field. Okay, so it has a little thickness to it and a certain radius. Now, so what I'm going to do is figure out the charge in here. And to do that, what I imagine is that I can cut this out and with like maybe a laser beam, and it's soft, like maybe made of putty, and I could open that ring up and it would form a rectangle. One dimension is the dr thickness, and the other is the circumference of that ring, 2 pi r, okay? And then the charge in that ring, the dq, will be the coulombs per meter squared times the meters squared of this will give me the coulombs inside here. So the coulombs per meter squared, that's the sigma q over pi r squared, total charge over total area. And the area of this is the area of a rectangle. The width times the height, 2 pi r times dr. So all this is the charge in here, which is the charge in here. So if I haven't already paused, let me stop here. I just explained the diagram. Now you try and jot it down to the best of your ability. Okay, so like I said, technically, if we were starting from scratch, we would have to figure out the electric field of this ring by integration. But we've already done it. So to shorten this video up, we're going to recycle the formula for the electric field of a ring. But this time we're calling it DEZ instead of EZ because this is just the electric field from this little part. We're obviously going to want the electric field from all the parts. So it's just a little bit of the net electric field. KQZ over this to the 3/2 power is the recycled formula from the electric field of a charged ring of a couple videos ago. So now what we do is we fill in the charge, which we figured out here, in here. And so that's the electric field by that ring. But we don't want just the electric field of this one little ring. We want it of the entire disk, right? The entire disk, not just a little part of it. So what we have to do is we have to add the electric fields of all the rings. A little tiny one, like almost radius 0. Then another ring, adding, till we all add up all the rings all the way to the outer edge of the disk radius r. In other words, when we're adding little tiny things over and over again, that's integration. So here we are, the total electric field in the z direction, integral from radius 0, oops, mistake, capital R. And then I just touched this up by taking the k, q, and the z, and they're all constants of throughout the integration, and then the pi canceled, and so I have r squared, and the 2 I left with the r dr because I'm already thinking ahead about the integration. And I brought this out of the denominator to the negative power. Okay, this is now a simple power. With the u substitution, we could verify that this, if it were u, all of this is du. So I won't do that because I don't want to bog down with too many details, but we could by letting this equal to u and then take the derivative and see that that's du. So all we can do is just power rule, add 1 to the exponent and make it to the negative 1/2. And then divide by that new exponent. So dividing by negative 1/2 is multiplying by negative 2 over 1. And I see I need to fix the limit here, capital R. All right, I don't think I paused yet, so let me pause and give you a chance to jot this down. Okay, now all we have to do is plug in our limits and solve. So let me put this off over here for later. All right. So KQZ over capital R squared, radius of the disk. Oh, sorry. Forgot the -2. And then I'll plug in capital R first. Okay, so what I have is 1 over the square root of capital R plugged in for R minus 0 plugged in to R, which gives us so this obviously is just 1 over Z, okay? What I'm also going to do is take this minus sign and the Z and distribute them here and here. And so this will be -Z over Z, which is just +1, okay? So oops. So again, this over here creates a +1. And then this over here creates a -Z over that square root. I hope you followed that and I didn't skipping that step wasn't too much. But there's my expression for the electric field of the disk. Okay. Let me pause and give you a chance to catch up. Okay. A unit check. Remember I say always, we want to compare it to our electric field formula of K coulombs, right? The coulombs constant times coulombs over meters squared. Well, if you look here, this doesn't have any units. We've got our K, our coulombs constant, then we've got coulombs over here, and we've got our meters squared over here. So far, so good. But what about all this? Well, this doesn't have any units, and this also doesn't have any units, because we have meters on top of meters squared, square root is meters. Meters on top of meters, also no units. So basically, we got some number over here times the right units. So the formula looks like it's of the proper form. Okay. The next thing I want to do is imagine what would happen if we had a disk that was infinite in size. And remember, I said infinite is a relative term. In fact, we could even consider this disk infinite in the right situation. And I say, well, you might be saying, this isn't an infinite disk. Not to you. But what about to an atom or an electron inside of an atom? So this is charged up. And now imagine we've got ourselves a little, well, we got nitrogen in the air, right? A lot of nitrogen, mostly nitrogen. So we got a little nitrogen atom here, which is like a little solar system with electrons orbiting around the middle, okay? So if we we have a nitrogen atom right here. As that electron is moving, one electron is moving from one side of the nitrogen atom to the other. That's such a tiny distance, that's the world of that electron, that to that atom and the electron in that atom, this disk is infinite as long as we're in this, that atom stays in this region. So this could be the infinite disk. But the key idea in that case is that R is much, much greater than the Z coordinate. In other words, we're somewhere confined here along the axis, and the radius is huge compared to how high we are above this disk. Then we could say this disk appears to be infinite, okay? What does the electric field become in that case? So let's do a little analysis. We're just going to play with this formula a little bit. And what I'm going to do is replace Q with first I'm going to replace K with what we use in Gauss's law for K, 1 over 4 pi epsilon 0. It'll just make something a little easier for us. So K is gone as long as we replace it, and this you could look up, it's a number. When you evaluate this, you get 9 times 10 to the 9th. So I haven't changed anything, and I've still got my 2Q over r squared, the radius of the disk, and then I have the rest of the formula unchanged. Again, in fact, the whole formula is unchanged. I haven't changed anything, I just put a new constant in. Now, this Q and this pi and this r squared are sigma, the charge concentration on this disk. Total charge over total area. And so what I'm going to do is rewrite the formula yet again and say, first of all, this becomes 2. So I could say sigma on the top over 2 epsilon 0 is all that's left if I replace these with sigma. And then I have this. Now, what we're going to do is allow the radius of the disk to be infinite compared to the z-coordinate. In other words, this is like, I don't know, it could be like 0.5 meters, and this is like 1 times 10 to the minus 10th or something. So this is like negligible, right? So we have radical r, which is just r in the denominator. So now we're taking a tiny number and dividing by a huge number. This becomes very close to 0. And so we have the electric field for what we would consider an infinite plane given just by this. The concentration over the disk over 2 epsilon 0. Now before I talk about that, I just want to mention that the units are proper, okay? Because K is basically the same units as 1 over 4 pi epsilon 0. So the 1 over epsilon 0 satisfies unit-wise Coulomb's constant K. 2 doesn't have any units, but sigma has units of total charge over total area. KQ over r squared, that has the right units. So we can say, okay, pretty likely that, that's a good formula. Correct. But what does it mean? What it means is if a disk is very large compared to your motion around the axis and you stay close to the disk, the electric field for any charge that can be considered like an infinite sheet is a constant value. In other words, if I'm like 1 millimeter above this disk or 2 millimeters or 3 millimeters, usually we say, oh, you're getting further away, the electric field getting smaller. But if the disk can be considered infinite, no. You move away from the charge disk and the electric field is staying constant. So that's the surprising thing that we see for very large surfaces. I also want to point out that, remember I mentioned the next unit in one of the videos, Gauss's law. So imagine we did 1, 2, 3, 4 chalkboards to get to this, figure out the electric field caused by a plane that could be, a charge that could be considered infinite on a surface. And in the Gauss's law unit, not 4 chalkboards, 3 lines. Boom, boom, boom. You get that done. So it's going to be nice in Gauss's law. Okay, so we're almost done. But what I want to now do is also figure out not just the electric field by this chart, but the voltage, the potential. Again, a reminder of what voltage is. It's the thrust per charge of something moving from point A to point B. Voltage is, or delta V, is the joules per coulomb of a charge moving maybe from one terminal of the battery to the other. But when you just get rid of the delta and you just have voltage, the path is not from one battery terminal to another, but the point and infinity. So what is the amount of electric field that we encounter starting from an infinite distance into some point around this disk? Well, one thing we could do is we could integrate this from infinity into some z coordinate. All right, we could do that, but we're not. The other thing we could do is use the formula K, Q over R, voltage of a point charge, and integrate over the surface. That's what we're going to do. So that's part 2. I'm going to recycle the diagram I have here. So you obviously don't have to redraw this. You already have it in your notes, earlier in your notes up above. So there it is. Now, we before used the electric field formula for a charged ring. But what we're going to do now is use the voltage formula. dV of this ring is K dq over R. Okay? And of course, R is not this R, but this R. And remember, if we don't have to prove it, we don't have to integrate, because voltage is a scalar. So for a ring, you could simply do this, that dV is K, the Q in this ring, which is all of this, and how far away is this charge from this point where we're trying to find the voltage? Well, it's this hypotenuse of this triangle, Z, R, this, okay? So that. Well, I think I had R squared first before. I guess it doesn't matter. So that's, again, just the tiny bit of voltage caused by this tiny bit of charge, the ring. But we don't want just the voltage of just a part of this disk. We want the voltage of the entire disk. So what we have to do is add up all these little voltages, starting from a ring that's tiny, almost zero radius, add, till we get to the largest ring of capital R. In other words, we're going to integrate that from 0 to capital R, and that'll give us the total voltage. So let me gather up all the constants, the K, Q, all the pi's go away, right? So and then KQR squared, and then the 2R dr, I'm going to keep, and I'm going to bring this out of the denominator, Z squared plus R squared to the negative 1/2. Once again, we could use a U substitution. This being U, take the derivative, solve for R dr, and you would find that this is all du right here. Okay, 2R dr is the derivative of what's in here with respect to R. So we could therefore just do the power with this U to the negative 1/2, and let me make some room. And if you need a little time, I'll pause to let you catch up. Okay, let's move on. So K, Q over R squared. Add 1 to the exponent gives us to the positive 1/2 now. And then divide by 1/2, which is the same as multiplying by 2 over 1. And evaluate that from 0 to capital R. So 2kq over r squared. And then okay, and so this is just z, so we can finally get our expression to do I want to write with square roots? I guess I don't have to. Okay, so there it is. Okay. Now, are the units correct? We could do a unit check. Remember, we need K coulombs per meter, KQ over R. Right now we've got K coulombs per meter squared. And then all of this is meters. Meters squared to the 1/2 is meters. So we have basically some amount of meters inside these brackets. And the formula seems to work out, okay? So that's the potential of a charged disk. Now, I just also want to point out that you could also get the electric field from this formula instead of what we did in the first part of our notes by deriving this instead and then taking the negative derivative of that with respect to z. And I'm not going to do it, but you could, and you would get the formula we derived in the first half of the video. So again, the electric field of a charged disk, we recycle the ring formula and find the dE and then integrate from 0 to capital R. And then for the potential, what we do is we do K dQ over R, the amount of charge in that ring, and then the R along this hypotenuse here, that KQ over R, and then we integrate from 0 to capital R again to get the voltage or potential of this ring. All right, so I'll see you in the next physics video.